What is going on, guys? My name is Hussein, and this is an old but gold article. Uber engineering switched from Postgres to MySQL. And this article was published on July 26, 2016, and this article explains why Uber moved from Postgres to MySQL. Back in the days, I remember that this article got a lot of backlash from the Postgres community and actually the whole database community, to be honest, because of how the language used in this article severely criticized Postgres as if it's a bad database, right? They don't even mention that thing, that they say, hey, by the way, guys, this is just didn't work for us. It doesn't mean it won't work for you. So that was the main reason this article was heavily criticized. I'm going to reference below this article and the Hacker News thread that explains that. They're just going to have a lot of discussions. Some discussions go into the deep, some discussions kind of point the flaws of this article. But what I want to do in this video / podcast is going to go through this article and through the main pain point that Uber had, and then discuss them, give you my personal opinion, whether I think Uber moving from Postgres, did they have to move from Postgres to MySQL or not? All of that stuff. How about we jump into it, guys? So, guys, first they explain that their architecture right here, they have the monolithic backend application written in Python that used Postgres for data persistence, and they're moving that, again, this is 2016, things can change, but they're moving to a microservices architecture, and surprisingly to a new system using schemaless. It's a novel database sharding layer built on top of MySQL. So we're going to talk about that a little bit. That is a little bit of flag. You might say, Hussein, what schemaless and MySQL? That doesn't make any sense, right? Exactly. That's a lot of people confused. Oh, okay. Why would you pick MySQL for schemaless? Just go with Cassandra, CockroachDB. I don't think CockroachDB was born back then. But Fauna, Mongo, right? Anything. But yeah, again, they have their own reasons. And that's another article. But what I want to focus in here is the architecture of Postgres, as they claim. So here's for the people listening, we're reading now the architecture of Postgres, and I'm gonna read the article, the 5 most pain point that led Uber to move from Postgres to MySQL. So this is the article now. We encountered many Postgres limitations. The first one, inefficient architecture for writes. The second one, inefficient data replication. The third one, issue with table corruption. Issues with table corruption. Issues, not issue. And there's the fourth one, poor replica MVCC, multi-version concurrency control support. And the fifth one is the final one, difficulty upgrading to new releases. I kind of agree with some of them because I use Postgres and I know how painful it is to upgrade Postgres. So I kind of related to that. I understand that this is a little bit easier process right now. But nevertheless, how about I don't agree with all the points, by the way, but I'm just reading out to you. I agree with some of them. Some of them is just, to me, preposterous. So how about we jump into it? So they look through the limitation and they decide to move to MySQL because it solves most of these problems. So how about we jump into one point after another. So the first point here, that's called the on-disk format. And they are describing in this article, in this section, the on-disk format of Postgres that implements a multi-version concurrency control. And we talked about it many times in this channel, how the actual indexes are stored, how secondary indexes are stored in Postgres. How do they implement a multi-version concurrency control using the transaction ID, the TID, right? and then max ID and min ID, and how a row becomes visible in my transaction. And once I go out of scope of the transaction, I need to do a vacuum to clean up those rows that need no longer seen by any other transaction. So that's all comes down to the isolation and all that stuff that we talked about many times in this channel. So check out the asset video here to learn about isolation, asset atomicity. I'm not going to explain it right here. So that's why I explain here. So what they are going through here is they have a table called users, and they're showing you how Postgres works. So for the people listening to the podcast, we're looking at a table with 4 columns: ID, first, last, and birth year. So first name, last name, and then birthday. And then there's an ID is a number, first name is obviously string, last name is a string, character, and then birth year. And they show you how this is on disk. And there's a CTID, which is a transaction ID that is stored. That's basically the tuple reference on the disk. And this is very, very important. So these tuples are A, B, C, D, E, F, G, and so on. And so the primary keys, they have an index on the primary key, which is the ID. They have a secondary index on the first, last, and birth year. So they have indexes on all of them. And again, this is just an example. They didn't show us their architecture for security reason, probably. So they don't show us their schema, nothing like that. But from this example, that tells me that they have a lot of indexes. So pay attention to that. So Postgres, their primary key and secondary key always point to the tuple ID, which is the physical representation on disk, right? And here's how Postgres works. So if you now go ahead and update a row, any row in this table, what we do is we essentially insert a duplicate row with a new tuple ID, this TID, right? And now that we have a new ID, we need to point the indexes, the secondary indexes, and pretty much everything that uses this tuple ID to the new representation, right? And that takes finite amount of time, finite amount of writes, and finite amount of work for Postgres to do, right? Because everything points directly to the disk, just like my ISAM in MySQL. That's exactly the same architecture where everything points directly to disk. And you might say, what's bad about this? There's good and bad. The bad thing is what they are explaining here is this: hey, the moment we touch any row, I have to update all the indexes, including the primary key, because now all these indexes have a new those entries have a new ID that I need to pick up, tuple ID. So I have to update that, and that obviously takes a ripple effect. They call it write amplification in the coming slides, right? And this logical write, so I updated a single field in a single row, yet it results on 5, 6, 7 writes, physical writes to disk, because you're updating this secondary index, this secondary index, this secondary. If you have a lot of indexes, this even gets slower and slower and slower, right? So bear with me here, right? So this is I'm just explaining their point now. So they go through all of that, exactly what I said, and that as a result slows things down, because first of all, writes are not slow per se, because you do a flush, right? You have a lot of writes to do, and then you do all of them at once. But the side effect of the writes, we're going to explain it in a minute. It's like one single thing translates to a lot of physical writes. Have to update this index, this index, this index, and this, and that. The write ahead log, which is something we're going to explain in this article a lot, gets large when you want to apply these changes. So that's the first thing. On disk, they go through the on disk representation of Postgres. Then they explain the second point is replication. And replication here, guys, as I discussed, the write ahead log is Basically, if I do an insert, if I do an update, this statement is translated into physical changes. Hey, go to this block and change this location and replace this value with this value, right? Or go to this index and change this value to this value. Go to this index on this position, change this. These changes are written in the write-ahead log as actual disk changes. Okay, so that's the very important thing to know. Now, this is the write-ahead log. We have this, and also write-ahead log has its own structure, right? It's somewhere else, and it's being maintained. So that's also the write-ahead log also has physical representation on disk when you translate it into an SSD, right? So there is a lot going on. So now, when you come to replication, which we talked about right here, guys, and also discussed it in my course, Introduction to Database Engineering, the idea of having a primary database accept the writes and standby replication for reads that can take reads. You need to push these changes, and the way you push them is you push the write-ahead log, which is a very consistent thing, down the standby databases so they can get up to date, right? So sounds simple enough. And what they explain here in the replication format, and this is where kind of their point about the limitation of Postgres is, you guys have this, first of all, you have this write-ahead log, which is quite large. Why? Because a single update statement translates into multiple writes, and these writes are made its way to the write-ahead log. So the write-ahead log doesn't have update this table. It's not like statement-based replication. Despite Postgres support statement-based replication through a third party, I believe, the MySQL have both supported both statement-based replication and also write-based replication. There is, again, pros and cons for both. So now, when we try to apply that, came back, the dog was barking. All right. So the master database pushes the wall changes down to the standby databases so they can get updated. But you might say, Hussein, what if the standby is actually executing a query? Do we just stop this query? Right? Let's say I'm executing a query in the standby to read something that happened to be deleted in the master, and it's being written directly. So I stop do I stop the query? Do I wait? All these questions are gonna get answered in a minute, and as a result, it will shape their decision to move to MySQL. I'm gonna explain it to you now. So now we talked about the on-disk representation. We talked about replication, and now we're going to talk about the consequences of Postgres design. That's the third point here, where the problems of Postgres. So let's enjoy this, reading this. The first problem is write amplification, and write amplification is apparently something is in SSD, where a single write that you think it's logical translate to many physical writes, especially in SSD. SSD does its own thing. So when you update versus insert, SSD does a little bit different thing. SSDs love to insert new things. You have to logically just insert new things and create new pages. SSD does not do well with updates, because the goal of SSD is to have a page and flush it. In order to update an existing page, you have to invalidate that existing page. You take it and then you copy it, change it, and then write it. So there is a little bit more work when it comes to an update versus an insert, which is faster. So that's all the reason why Google invented the LevelDB database, and then why Facebook invented RocksDB on top of that, I think. that to take advantage of SSDs, and they built a completely different structure called the log structured merge tree, where it's optimized for inserts instead of updates, right? So everything is an insert almost in the log structure merge tree. So that's the idea of write amplification in SSD. Now take that and amplify it at the Postgres level. I, as a client, I'm doing a single update statement to my table. And if I have like 700 indexes, I just made 700 updates, physical updates, as a result of my single logical update. So that this 700 updates also at the SSD level translate to many physical amplified SSD updates, because you going writes and pages, and SSD, poor thing, they have a limited shelf life. So if you have a limited shelf life SSD, you can only write so much. I think there's a number that varies between a disk and another, but in general, it's essentially, I think, 12,000 times or something like that. That's most of them. So yeah, so they explain this here. I just summarized it to you. Write amplification is a problem for them. So their SSD is getting their lifespan of SSD is getting lower and lower because of the write amplification, because those guys have hundreds and hundreds of indexes. Why would you have this much indexes? Beats me. Do you really query on all of them? Do you really query on first name, right, or last name? That's why adding indexes is great. Adding too much indexes is just a bad idea. So that's the write amplification problem. The second problem they want to discuss here is the replication problem. Guys, take the same thing that we did. We did a single update that translated to lots of update to all the indexes, because all of the indexes point to the row directly. So, and the row ID changes, so we have to make them aware of this row changes. So all of these indexes point to the row directly. So these changes are just amplified. Now these changes translate to what? To a wall, right? Write ahead log. Hey, update this physical index and this index and this second and this. And by the way, there is a row here, change this value to this, and there is it's all physical write to the disk. What they complain about in their applications is this wall translates to a large, big sized bandwidth when it comes to their master worker or standby replication. And those are interstate. They have their replicas across states, across different countries. So they had to buy expensive bandwidth to kind of transmit their wall changes from this replica to this replica. And I believe they have also grandchild replication, so take that into consideration. So the wall changes as they grow large, the bandwidth becomes expensive because they are very large, and they're not making small updates, they're making large updates, which translates to even larger. So that's the limitation problem here. In case I'm gonna read this section for you guys, so you can learn more about it. In case where Postgres replication happens purely within a single data center, the replication bandwidth may not be a problem. Modern network equipment and switches can handle a large amount of bandwidth, and many host providers offer free or cheap intra-data center bandwidth. Right. If you are internally, I can transfer 1 gig of wall sizes easily. However, when replication must happen between data centers, issues can quickly escalate. For instance, Uber originally used a physical servers in co-location space. I don't know what the heck is a co-location. Co-location space on the West Coast. For disaster recovery purposes, we added servers in second East Coast co-location space. In this design, we had a master Postgres instance plus replicas in Western data center and set of replication in Eastern one. So that kind of the constraint you can see from east to west, just just did not scale for them, right? Because of that. See how one single problem can lead to a lot of bigger problems, can lead to another problem. You see the pattern, guys? Writes are big because they have a lot of indexes. That's where you should start. Why do you have this much indexes? You might say, hey, Hussein, I cannot live. I have to have 350 indexes on all my fields because I query against them. Well, in this case, I was like, okay, maybe that's not a choice for you then. But try to avoid that in the first place. That's what I didn't see, and that's why people are pissed. It's like, wow, didn't you explain why do you guys have a lot of indexes? Can you explain why do you need? I bet if you go into the actual architecture, most things don't need this much indexes. As a result, you will not translate to a huge write amplification consequences. You will not have that because you will not have a lot of indexes to update, right? But, well, we're not an Uber, so we don't know their architecture, but that might be a valid use case. So let's go to the data corruption. This is the most dumb section in this whole article. I'll save you some time. What they say here is, hey, during the replication, Postgres 9.2 had a bug in it, and our table was corrupted as a result. Seriously, Uber? What software doesn't have bugs? You're adding a bug as a result to move from Postgres to a MySQL? Like MySQL is perfect? That's just odd. That's just, to me, I'm sorry, that's just odd. So they said during the replication process, the replicas were not in sync for some reason, and as a result, when you query for a unique value, let's say select star from users where ID equal 4, you should get 1, right? They were getting 2. They were getting the old retired row for some reason. Right, and that causes their application to fall down and then fall apart. So they had to add defensive programming and to catch for this stuff. But it's a bug. Postgres immediately, if they notified Postgres team, they would immediately have fixed it and fixed that bug immediately. But that's a good bug. But I don't see bugs as a reason to move from, as a kind of showstopper, in my opinion. So they talk about that, and they talk about here, one section is the B3 rebalancing, which is, by the way, B3 rebalancing adds to the write amplification. They don't mention that, but it's just implied because a lot of people know that when you insert to a row and you have a lot of indexes, you keep updating those indexes naturally if your value touches that index, right? However, as a result of inserting, the B-tree structure might need to rebalance itself. And when it needs to rebalance itself, it actually doesn't physical update to the tree. And updates are updates, not inserts, right? So updates translate to what? To actual SSD write amplifications, because SSD do not like updates. So that's another thing that can amplify the writes. I'm talking if you go to the millions of rows, right? Obviously. Right. Let's move to the next one. Replica MVCC. All right. Replica MVCC, or Replica Multi-Version Concurrency Control. It says, Postgres does not have true replica MVCC. Well, why? Because the fact that replicas apply wall updates directly, right? Because if you think about it, Postgres by default, takes the on-disk representation of the wall changes, and that's what gets transmitted. So it's often higher bandwidth, but if you think about it, it's faster, right? The alternative is just do statement-based replication, right? Where instead of sending the results of the execution of the queries, send the queries themselves. Like, hey, I just did an insert, I just did an update, I just did an. So the actual string of the statements, these SQL statements, just send them to the replica. This will be way slower, right? Because yeah, the bandwidth of transmitting these wall changes as form of statement is smaller than the actual physical changes that happen. However, applying them to the replica, now you have to actually, inserts are not, straightforward inserts might be okay, but what if you do an update, for example? An update could scan, could touch the index, actually does work. So you did double the work technically, right? Because you did the work to execute the statement on the master. You now are doing the same work exactly, and if that statement is expensive, you're gonna take the same cost on the server and at the destination. So there is a pros and cons for using both, but they're complaining here that Postgres wall update is just doesn't give them MVCC support. So let's claim that. So let's say if I am in a replica standby and I'm executing a query, and one of my wall changes affects that query that is being executed on the standby. So again, I have a master. I deleted, let's say I deleted a table. That's just a little bit harsh, but let's say deleted a few rows, right? And now on the standby, I'm actually querying those rows that is being deleted on the master. I am on a different replica. So now I am pushing the master, pushing the wall changes to the standby, while that query that is querying those deleted rows is being executed. What should Postgres do? You tell me as the viewer, listener. What do you think should happen here? Should the Postgres immediately cancel the query, right, and write the changes, or should the wall changes be paused until the query finishes? If you think about it, there are no other choices, right? You have to pause it. Obviously, you're not pausing all wall changes. You're only pausing changes that affect running transaction, and that's another thing to worry about. How the heck do I know that the query that is being executed actually affects my wall changes? Building databases is not easy, guys. Look at all this complexity. So they're complaining here that you guys don't have VCC support because what you're doing is, what Postgres does effectively is essentially having a timeout. It says, hey, we're gonna block the wall changes for a given timeout, and they give you this timeout configurable. If the query didn't finish in this amount of time, we're gonna cancel those changes. We're gonna cancel the query that is actually querying, it's reading, and while we're applying, we're gonna force applying the changes. Why? Because Postgres design favor eventual consistency over, let's say, just reading queries, right? In this case, right? So I rather be eventually consistent. Remember, this is eventually consistent as well. So stop saying that NoSQL is the only database has eventual consistency. Every database has it, as long as between replicas, right? Relational doesn't. In the same instance, yeah, it's completely consistent, but across replicas, there is always this idea of eventual consistency. So what Postgres does is actually kills the transaction, and they did not like that. So guys, let's read this a little bit. I kind of don't agree with this statement, right? The design means that replicas can routinely lag seconds behind master, obviously, and therefore it is easy to write code that results in kill transactions. What does that mean? This problem might not be apparent to the application developer writing code that obscure where the transaction started in. For instance, say a developer has some code that has to email a receipt to a user. Depending on how it's written, the code may implicitly have a database transaction that holds open until the email finishes to sending. That's just a bad idea, right? You don't hold a transaction open and you do stuff has nothing to do with the transaction itself. Try to avoid that as much as possible. So that's just a best practice. While it's always bad form to let your code hold open database transaction while performing unrelated working I/O. Okay, thankfully they mentioned that. The reality is that most engineers are not database expert and may not always understand this problem. I have to disagree with this one. Again, guys, if you know me from this channel or the podcast, you know that as an engineer, you have to take pride of your work and the thing that you interface with. I believe that you have to understand what you're communicating with. So yeah, engineers are not database expert, but this does not qualify as a database expert. This is just basic transaction management, in my opinion, right? And I believe engineers have to understand this, right? And engineers have to understand. If you might be not as radical as me. I don't like to work with anything that I don't understand. If it's black box, I don't like to work with it. Before I pick a tool, I have to understand fully how it actually works. Fully from 0 to 100%. If I'm working on it, if I'm connecting with it, if I'm interfacing with it, it's okay if I understand 80, 70% of the tool, right? But again, I'm not going to understand every single thing in that case, right? But that's just me. You might have a different opinion. Postgres upgrades. So I kind of agree with them on this one. I tried to upgrade Postgres many times and always didn't find the right tutorial, or it was so complicated that I gave up, right? And they kind of reiterate the same problem. So, but I had to agree with them 100% on this. Postgres upgrade is really painful. Really painful. I've been there. I've been there from 9.3 to 9.4, 9.4 to 9.5. I then just gives up. I just rather recreate my databases from scratch after that. Obviously, I'm running a test database here, but yeah, I didn't run a production database that I had to upgrade it. But what I'm going to do in this case is just, obviously, there is a way, but apparently this way sometimes works, sometimes it doesn't. So there is also the PG logical way of I think there's some tools that allow you to do upgrades, right? And guys, if you know any of that stuff, if you have ever upgraded Postgres database smoothly, let me know in the comment section below. I'd love to know how to do it. I tried twice, I believe, and I gave up and says, you know what, this is not straightforward. I wasn't forced to do it, so I took the easy route of recreating my data. Okay, the architecture of MySQL. AnyDB. We talked about AnyDB, guys. Check out the video right here if you want to learn more about it. But AnyDB, so they go now through their own disk representation compared to Postgres. So AnyDB or just MySQL in general. MySQL or AnyDB in general, that's the right way of saying it. They have the primary key. And the primary key has a pointer to the row directly, to the physical database on the scroll. All the indexes that you create points back to the primary key. And that's the powerful thing here for them. Because now, if I update anything on the row, only the primary key needs to be updated to know the new kind of row ID. And even that, right, it's a little bit different. But I don't have to touch my secondary indexes, right? That being said, guys, that's not always true. If you're updating a field that has no index, then, right, you're going to not touch only the primary key. But if you updated a field that has an index, you got to touch both. So they didn't mention that, but yeah, right, because it's very defensive article, right? MySQL is perfect. Yeah, if you update the actual field that has a secondary index, you have to update the secondary index. You just updated a value. So you have to go to your index and change the tree so that includes this value, right? So yeah, you touch a lot of fields, right? And if you touch a lot of fields, yeah, then you have to update all the indexes, right? It's just by design, it's less. If you have a lot of indexes, you have less changes in general, right? So as a result, this translates to obviously less wall changes because they don't have as much changes, logical to physical translation. And now they talk about the rollback mechanism here. That in MySQL they have this concept of rollback segments. So instead of inserting a row in the heap itself, when you update a row in a Postgres, you insert a row in the heap itself, in the table itself, right? MySQL and InnoDB does it differently. It's just they copy the row into some other place called the undo, the rollback segments, the undo logs, right? And they keep it all there. And then based on that, they point to that location in the rollback segments, right? So it's a little bit different architecture. So if you query now, if you want the latest is always there. So that's the beautiful thing. But based on your transaction ID, if you are coming from the past, you are querying in the past, you want older results, you have to do the jump to go back to get the older done. This jump doesn't exist in Postgres. So queries that are concurrent are faster on Postgres. They are technically slower in MySQL because now you have to jump back and go through different places to do the query, right? And vice versa. So they explain that, hey, secondary indexes point to the primary index and the primary index point to the disk. This is for people listening on the podcast. We're listening, we're watching, we're listening. We're looking at a picture of secondary index pointing to the primary index, and then primary index is pointing to the disk. Right? That's just an extra layer. And then they claim that they say here that the replication section of MySQL supports multiple replication mode, statement-based and wall changes. And the moment if you implement any of these modes, if you implement statement-based replication, you have true MVC support, because now the statement, the wall changes that is coming to you from the master to the standby is just another write. Consider it another transaction trying to be executed. So it will have true MVCC support at that case. It will not be blocking, right? Because you can technically query and write at the same time. And now as a result, you can implement the same exact thing that you're doing, right? Because you have logical view of what is changing. As a result, the database is aware of the change. It can implement MVCC at the higher level, right? Even through replication. Postgres does support that. There is a third party that you can install and does exactly that. You can do that. It's just they just didn't mention that. Again, guys, this is an old article, so things can change, obviously. Right. In MySQL, and they say that, oh, by the way, even the wall says the wall sizes are so small because we're changing very few things here. They go through all of that stuff again. I'm not going to go through that, but that's essentially their advantages. They go through another advantage here of MySQL, saying that the buffer pool is the caching mechanism in Postgres compared to buffer pool is the caching mechanism in MySQL compared to the caching mechanism in Postgres, which is basically the RSS memory, right? And they're explaining the difference here. They claim that Postgres uses a different operating system calls, like they're using 2 calls instead of 1. I don't know much about that, to be honest. I'm not an expert in operating systems, but a lot of people say that, yeah, you have to use a 1 call to seek and read at the same time instead of seeking and reading. I don't know. Maybe Postgres actually changes. A lot of people here listening and watching this channel, some people actually are experts in this thing and might correct that part, but I'm not aware of that as a result, so I can't comment much on that part. There is then the InnoDB storage engine implements the least recently used buffer pool, and which you can apparently control. I'm surprised that you cannot control the cache size on Postgres. I need to read more about that a little bit. But that's another thing they said, oh, this is another advantage of MySQL. Then another thing says the connection handling. In MySQL, there's a thread pair connection. Each TCP connection you open to MySQL is a thread on the server side. However, Postgres, it's a actual process. So technically now they claim, obviously, a thread is cheaper to spin off than a process. I read that this is no longer true because a process and a thread is almost identical now. But could be back in the days, could be that was true. But now, if you think about it, to scale 10,000 connections right now, if you think about it, opening a lot of TCP connections is just a bad idea. So that's why we have the idea of connection pooling, right? We build our application so that it uses a pool, reserve a pool, reserve a connection from the pool, execute the transaction, and then return it to the pool, right? And if you're doing a single atomic statement that executed, you can just execute on the pool directly. Say, hey, pick any pool, any instance in the pool, execute, and then return it immediately. Right? This reserve and release is also back to their queries. If they have a queries that span 3, 4, 5, 7 minutes, and again, nothing wrong with a query that transaction that stands long if you're actually doing all database works. Some transaction, I've seen transaction that takes 30 minutes just because it does a lot of work. It changes a lot of stuff, and these changes has to be atomic, right? Yeah, you can argue that you can break it. Even that, you have to break these transactions into smaller and smaller pieces, so that each piece can be executed in its own atomic manner, right? So you can minimize the transaction size. So this also results in, if you have a long-running transactions, then you have to really think about how do the reservation and connection pooling works, right? So the number of connection, right? Think about it so that if a client's not using a connection, then don't let them open a connection and just have it open. Use connection pooling, and they say they use I believe PG Bouncer. Is that what they're using? Some service that actually does that connection pooling. But a lot of applications do it. Even if you don't, you can build your own layer on top. And I showed connection pooling on Postgres many times in this channel. Right, so that's the idea, guys. And hopefully in the future, we're at the end of the article, obviously, guys. Right, we're at the end of the article. But hopefully, when it comes to connection pooling, I really hope that Quick as a protocol, and Mask, I believe that they're just working on a new protocol right now. It's called Mask, that will allow you to kind of stream open multiple streams on a given TCP connection or UDP connection in case of Quick, that represents your database connection. So that if MySQL or Postgres supported Quick, and I don't see a reason why not, then the client can open a single, and remember, the client is always a web server or something like that, right? So you can open a single connection and have up to 200, even more than that, streams concurrently in a single TCP connection. The only trick here is the database has to understand the idea of streams. So that's a lot of work, but I believe it's going to be really lucrative for a database to implement a protocol like that. Just like I don't really need TCP anymore, right? A single TCP is just a wasteful thing to have a single TCP connection for a given client, right? Or connection pooling. This has to go away, and we have to move to a model where we multiplex queries in a single TCP connection using this protocol, right? Whether you're using, even if they implemented their own, they don't have to use Quick. You just implement your own protocol that supports multiplexing, through multiplexing, so that every request, every session, every channel has its own logical representation in that TCP connection that you open. So this way you don't have to open many connections. You just have to open one or few of them, and each one of them has basically some limit. Obviously, that doesn't come with for free, because now you just increase the CPU size at the back end and the front end, because now you have to assemble these channels and streams. That's the problem with HTTP2 and Quick. People start, Lucas Purdue and what's his name, Chris Wood, and people working on the Quick protocol. They're trying to solve this problem with the CPU usage, right? Because CPU usage, now you're just not working with just stream of content coming from the TCP socket. No, you have to actually look at the data and then arrange the packets so they are in logical streams or channels, and then deliver it to the app. So the operating system or the application, wherever this thing lives, doing extra work. So again, I'm sorry about that segue, but I want to discuss that a little bit. I think that's just an idea that is just great. Conclusion, obviously, they say, hey, Postgres served us well in the early days of Uber, but we ran into significant problems scaling Postgres with our growth. Today, we have some legacy Postgres instances, but the bulk of our databases are either on top of MySQL, typically using our schema-less layer. That's another point. You have now schema-less. You have schema-less and using MySQL. Maybe there is something I'm missing here, but it does not seem natural to me. A lot of people use Postgres as a schema-less layer, where they put a hunk of JSON in a single field as JSON B, and they work with that. But maybe that's just the way for Uber, because if they have a lot of fields and they have a lot of indexes on those fields, maybe that's the way to go. Who knows, right? Again, guys, what do you think? What do you think about all that stuff? Let me know in the comment section below. I'm gonna see you in the next one. Hope you enjoyed this video. Give it a like if you do, and share it with your friends. I'm gonna see you in the next one. Thank you, Ivan Kiltizicki, a staff engineer in Uber Engineering. This is a great article again. Yeah, and things has been changing a lot in the Uber world. But this is a historical article that goes in the years and years, and we had to discuss it. So thank you so much. Appreciate you. I'm gonna see you in the next one. You guys stay awesome.